Um, what we will do is we'll first go through uh, the solutions for quickly go through the solutions for the midterm. Did you guys go back and go through each question? Did you realize where all you did mistake or no? You did? Okay, all right. Okay. Okay. This one. I quickly looked at your answers, so it looked like all of you got most of these wrong. Okay, but let's start here. Definition is okay. Definition is okay, but the examples were a problem. One of you had written 0, 5. The set was a vector space. Is that a vector space? How will you verify if it's a vector space? Sorry? You'll have to be louder. Zero vector is there, but just because the zero vector is there does not mean it's. If it's not there, of course you can say, okay, it's not a vector space. Zero is there, so it could be a vector space. What else would you do? Okay, is this closed under scalar multiplication? Huh? Yes. Okay. So how did you verify that it's yes? Yeah. How do you verify it? So if I give you a set and I ask you verify if it's closed under scalar multiplication, how would you verify it? Sorry? Multiply what by a scalar? You take any one element. So you multiply all the elements, is it? See, if you say you multiply all the elements, you still have to do the multiplication one by one, right? So you take one element, multiply it by a scalar, and then do what? No? You're not sure? So what does it mean to be closed? If I take an element from here, I multiply it by a scalar, you say it's closed under, well, let's say I claim that this set is closed under scalar multiplication by alpha. I'm only making this statement. I'm not making a general statement that it's closed under scalar multiplication. I'm saying it's closed under scalar multiplication by a scalar alpha, some fixed value. That means if I if I take any of the elements, multiply it by alpha, that resulting element will be there in the original set. If that is true for this fixed value alpha for all the elements, then you would say it's closed under scalar multiplication by a fixed value alpha. But if you say it's closed under scalar multiplication period, that means no matter what scalar multiple you take, if you take any element from the set, multiplied by any scalar, you will find the resulting number in the set. That's what it means to be closed. Okay? So I ask you again, is this closed under scalar multiplication? Okay, whenever you say something is not satisfied, right? All you have to do is give one example where the condition is not satisfied, then we know it's not satisfied. Why are you saying it's no? If you say no, you'll have to give me an example. If you say yes, you'll have to give me a general argument why scalar multiplication is satisfied, because there are infinite number of elements in the set. Of course, you cannot show every that the thing is satisfied for every element. You'll have to show some. You'll have to provide some general argument. You're saying it's not closed. I'm asking, give me a counter example. An example that shows that it's not closed. Then it's not closed. That's all over. If you take 5, I multiply it by 2, 10 is not there. So this so this is not a vector space. Okay. Why is there so much difficulty in understanding this? I genuinely want to know, because closed property of being closed is fairly simple property. That means vector space, verifying if something is a vector space is also fairly simple to do. Where is the problem? So what confused you as to what closed means? I'm not asking this to criticize you. I want to genuinely understand where maybe in our instruction we've gone wrong, that the idea was not clear. Not sure? All right, fine. Let's continue. So this is not closed under scalar multiplication. So that means it's not a vector space. So we don't have to verify anything else. So this is out. So this example was wrong. I mean, all you had to do was simply say Rn, because we've already seen examples of vector spaces. So I was expecting you'd give something like this. If you had said set of n cross m matrices were a vector space, that would have been even nicer example. Or if you had said set of functions x, set of continuous functions f of x, or something like that, that would have been even nice. This one, definition everybody got right, because you just had to remember. What is an example of a subspace? To give an example of a subspace, you'd have to start with a vector space first. But one simple example is just the zero element. Zero element is always a subspace. Just a trivial subspace. What about this? What is a linear transformation? No? Okay. All right. This is any function that maps from Rn to Rm, which satisfies the proposition. Okay. In fact, if you had simply written x, where x is from Rn, this is from Rm, and this is a m cross n matrix, this is an example of a linear transformation. What is the rank of the matrix? Sorry? Yes. Yeah. Okay. Symmetric matrix, most of you got. Some of you had done at least one of you had done a mistake. It's skew symmetric matrices. I think the person had written something like this. Is this skew symmetric? What is the condition for being skew symmetric? What is the definition of a skew symmetric matrix? Yeah. Yes. A transpose equals minus A is the definition. What is the transpose of this? 6, 4, minus 4, 6. Is that equal to minus A? Minus A would be minus 6, 4, minus 4, minus 6. It's not equal. What would you change in this matrix to make them equal? Yes. For a skew symmetric matrix, the diagonal elements is 0. Okay. Again, inverse, nobody got. What is the inverse of a matrix? Inverse of a full square rank, square full rank matrix. Yeah, good. Yes. Sorry. Yeah, inverse of a n cross n matrix is any n cross n matrix, right? Such that AB equals BA equals IN. That's all. That's the definition of an inverse. And in fact, that B is usually represented as A, written like this. And when we're asking for an example, all you have to do was give 1, 0, 0, 1. This is I. This is the inverse of itself. If you're just done that, that's fine. What about this? What is the column space of a matrix? Sorry? Yes. Span of the columns away. How would you give an example? Well, you could have just done this. Let's say this is a matrix. It's just a column vector, but still a matrix. Then all elements of this form, where alpha is any real number, is essentially the set of all is essentially the span of the columns of A. So this is the column space. Null space? What is the definition of the null space? So if you have a matrix A, set of all vectors x such that Ax equals a zero vector, where A belongs to n cross m, x belongs to. This is essentially the set of all. That's the definition of the null space. Right? Example, you could have just given this. If this is my matrix A, then all elements of this form, set of all vectors of this form the null space. Because if I multiply, this is A, this is x. If I do x, I'll always get 0. Actually, question I and J were the same question, just worded differently. Homogeneous solution, I should not have said matrix. Homogeneous solution of Ax equals V is essentially the null space. Yeah, if you're not able to provide an example, right, then that means you don't understand it. Okay? Use that uh, as a way to gauge your understanding. Okay. I've not looked at these, but I assume most of you got these right. What is A2 transpose? A2 transpose A4. What is A2 transpose? What is A2? Yeah. Yes, second column of A, inner product of that with fourth column of E. So you take the transpose of this, and then you take the inner product with this. What about this? Yeah. Sorry. First row written as a column, correct? Okay. So that will be 1, minus 1, minus 1, 0, 2. And fifth column written as a row. 2, 3, 5, 5. What will you get if you multiply these two? Can you multiply these two? You can? See, you have, if you do this, I don't know if it's yes or no. What is it? Okay, just verify. Because you're not comfortable yet, I would say just write down the shape and see if the conditions are satisfied. Yes, okay. You can multiply because it will be 5 cross 1 multiplied by 1 cross 4. What will you get if you multiply? Yep. Sorry. A 5 cross 4 matrix. What will it be? You should be able to say that without having to do the computation. What will be the first column or the first row, whichever you're comfortable with. You have to be louder. Yeah. Second row. Same. All 0. That's all. Okay. What about this? So you'll have to write down the matrix and then say what the shape will be. Can you quickly say the shape without even writing it down? Sorry? 1 cross 2, is it? Why will it be 1 cross 2? You're correct to say that it's 1, but cross what? What have we done? What is this? Not 1 cross 1, no? 1 cross 5, right? And what is this? So what will the resulting matrix be? 1 cross 10, no? There'll be 10 elements. The two rows are kept right next to each other, so there'll be 10. This will be 1 cross 10. Okay. What about this? If you multiply this, right, what will you get? Will you get a matrix or a scalar? Scalar, okay, that's correct. And what will you get? Or, yeah, you tell me what you will get, and then let's see if we can understand what X transpose AY is without even doing the calculation based on the fact that we are given X and Y. Okay, what will you get if you multiply A and Y without even doing? Huh? Great. Okay, you'll get the third column. And then what are you doing? Yes. What are you doing then? Exactly. So if I asked you to explain this in words without doing the computation, what will you say? What is this entire thing doing? Yeah. What is it? Not all the columns. Yes. If for this X and Y, this whole thing essentially comes down to adding the elements of the third column. That's it. Okay. If you got that, then you should be able to tell me if I want to add all the elements in the matrix A, okay, and I want to represent it as a matrix multiplication operation. Let's say I have a program that does matrix multiplication very quickly. So if I can express this operation of adding all the elements in the matrix as a matrix multiplication operation, then the computation is very quick. If that is the case, I am asking, can this process be expressed as X transpose AY for some appropriate values for X and Y? Can we do it or no? We can. Okay, what will be X? What will be Y? X will be 1. So what will be X? You can tell me. 4 ones, is it? Okay. What will be Y? Huh? That's all. Because if all the Y's are 1, what does AY correspond to? What operation is it doing? Without doing the computation, can you tell me if the Y's are all 1, the components of Y's are all 1, what does AY do? Sum of what? AY, man. You're right, sum of something, but it's not rows. If you post multiply, you're taking the linear combination of the columns of the matrix, right? So you're essentially adding all the columns. And what is X transpose Y doing then? Well, it's if you pre-multiply by a row, you're taking the linear combination of the rows. You're adding all the rows of AY. Okay. Or if you look at it the other way around, if you do X transpose A first, then you're adding all the rows, and then post multiplied by a column vector, which is all 1. That means you're adding all the columns. Yeah. So if you choose X and Y to be this, then you essentially X transpose AY is essentially adding all the elements of. As a side note, let me ask you this. Let's say I want to what will happen if I choose X to be EI and Y to be EJ. And remember, both of these are from different spaces. This is from Rn. In fact, in this case, this is from R4. This is from R5. Without doing the multiplication, can you figure out? That means if I do, what will happen if I do EI transpose A, EJ? Maybe even more specific. I'm doing E2 transpose A, E4. What will I get if I do this? Okay, I'll leave it as an exercise for you to do, but it's worth thinking about. In fact, an extension of this is, I would say, let's say you wanted to express, you had a matrix A and you wanted to add Aij with ALK. Can you express that as X transpose AY? Okay, something for you to think about. Right, okay. The last one. So the first question is, are the columns linearly independent? How do you find out if the columns are linearly independent? Sorry? Right. You cannot express any one of the columns to be linear combination of the other columns. But how do you verify? That's the definition. Sorry? Sure. Okay. So correct. That's the way to do that, right? In this particular case, do you have to do that? Do you have to do that alpha times and then find the all alphas and see if all of them are equal to 0? Do you have to do that for the columns is my question. See, if you have vectors from, if you have a set, right, whose elements are from Rn, okay, and I tell you that there are n plus 1 vectors in this set, and then I ask you, is this set linearly independent? What can you say in that case? Again, going back to the first module, if you're talking about vectors from Rn, the maximum number of vectors that you can take from Rn and still form a linearly independent set is n. The moment you take n plus 1, for sure the set is linearly independent. Okay, so here, this is essentially a question to test that. You didn't have to compute the alphas. The columns are all from R3. There are 4 columns. For sure, that's linearly dependent. So this was, yes, in fact, no, the columns do not form a linearly independent set. Or another way to think about it is rank. What is the, can you say about the rank of this matrix? Well, you don't know the rank, but what can you say about the rank? If this, since this is a 3 cross 4 matrix, what can you say about the rank? Is minimum what? Sorry? Okay, so what will be the, what can you say about the rank? No. It will not be 3. You know for sure it will be less than or equal to 3. It will be between 0 and 3. Okay. How many columns do you have? Okay. Then I ask you, can the columns form a linearly independent set? Because the definition of the rank is, what is the definition of the rank? Sorry? Number of linearly independent columns or rows that you can choose. That means you here, because you can only choose 3 columns and still be possibly linearly, that can possibly be linearly independent. Here you have 4, that means it's linearly dependent. So the first question was essentially, you didn't have to do anything, you just have to know this fact. What about the rows? Well, here, unfortunately, we don't have any help. The rank can be 3. There are 3 rows, so it can be full rank, it can be, or it can be rank deficient. Here you would have to essentially solve for that alpha and find out whether or not it's linearly independent. And then I don't think all of you solved this, which is again was surprising. X equals, because we went through this whole thing now, getting it to the reduced to echelon form, and then finding out the particular solution and the homogeneous solution. You just have to repeat that for this matrix. But it looked like, why is that? You didn't practice Gaussian elimination, is it? Why not? It's very simple, no? So, okay, let me put it this way. What about Gaussian elimination is still confusing for you? That you did not attempt it. You just did not have time to prepare, is that right? Well, let's assume it's like that. Okay, fine. I would say, then I'd say, please go back and try and solve this. Go back to the lecture, view the lecture. If you're still not sure how to do it, go through the procedure and then find out the full solution. And then once you do that, then you should be able to find out what the null space is. The null space is essentially the homogeneous solution. Okay. Right. That's all I wanted to say for this. Are there any other questions about the midterm? Okay. Now we move to essentially maybe the second part of linear algebra. We're done with the x equals b. Now we're going to look at other aspects. And this particular lecture is again is on a very important topic, which is on orthogonality. Which is about this idea of two vectors being perpendicular to each other. Okay? And when they are perpendicular to each other, one way to think about them is they essentially don't share any common information. If they're not perpendicular, then you can say they assume that direction tells you has some information. If two vectors are perpendicular, then one way to think about it is they don't contain any mutual information. Okay? But if they are not perpendicular, both of them have some common directionality. That means they share some common information. That is why this idea of orthogonality is very important. Right? We know the definition of when two vectors are orthogonal. If you have two vectors x and y, right, from Rn, we say that the two vectors are orthogonal if their standard inner product is 0. This we already know. This is for two vectors. Okay. Now, instead, let's say you had a set of vectors. You had a set of vectors v1 to vr, and again, we'll assume each of the vi's is from Rn. We say that this set, that this is a set of mutually orthogonal vectors if and only if this condition is satisfied. If you take the inner product of any two vectors that are not equal to each other, and if you get 0, then you say this is a set of mutually orthogonal vectors. Let's look at an example. I ask you, is this set mutually orthogonal? I'm going to call this set S. Is the set S a set of mutually orthogonal vectors? Well, there are only two vectors. It's easy to verify this. You simply take the inner product of these two and verify with 0. If you take the inner product, it will come out to be 0. Okay. So this is V1, V2, V1 transpose V2 is 0. That means it is mutually orthogonal. Now, if I go and add a third vector, is this still mutually orthogonal? Yes. Yes. You essentially not done anything by adding the 0 vector. Okay. So it's still mutually orthogonal. Now? No, it's not. Oh, it's not mutually orthogonal. That's all. The way you verify is if I take two of them, if I take their inner product, and they have to be distinct vectors. They can, of course, they cannot be the same vector. Because if it's a non-zero vector, so for example, if it's a non-zero vector, if I take the inner product of it with itself, what will I get? No, there is a specific meaning to that, right? If I take Vi and I take the transpose inner product of Vi with itself, what do I get? Nobody's looking at me because nobody knows, is it? All right. The square of the second norm, the Euclidean norm, or the Euclidean length of the vector. So of course you should not do Vi transpose Vi and expect it to be 0. It will be 0 for the 0 vector, but for any non-zero vector it will be non-zero. So the condition does not include that. I has to be not equal to J in this condition. Okay. Now let's say we do have for now, let's say when we talk about a set of mutually orthogonal vectors, from now on, we will not include the 0 vector. I included the 0 vector just to demonstrate that if you add the 0, this condition is still satisfied. Let's say when we talk about mutually orthogonal vectors, we're always talking about vectors where the 0 element is not there. That means the inner product of each vector with itself gives you a non-zero value. Okay. If that is the case, if I have a set of mutually orthogonal vectors, is that set linearly independent? Is the question clear? It is. Right? So it turns out it is. Okay. Let's say we start with the set. What is the condition for, let's say we're talking about this set, and let's say it's it's a set of mutually orthogonal vectors. Right? To verify if it's linearly independent, this is what you would do. And you would ask, well, all my alphas equal to 0. The only way I can produce 0 on the left hand side is if all my alphas are 0. Okay. You can show this easily by simply using the property that the set, it's a set of mutually orthogonal vectors, and none of the vectors are the 0 vector, because if there is a 0 vector, of course it's linearly dependent. Okay. So we will not consider that case. Okay. If I have this, right, let's say I take the inner product of this on both sides with V1, let's say, right? V1 transpose alpha 1 V1 plus alpha 2 V2 alpha R VR, and I do V1, this is the 0 vector, V1 transpose 0 vector. The right hand side is still 0. But in fact, right hand side is not a zero vector. In fact, it's a scalar zero. Right? On the left hand side, what you will have is alpha 1 v1 transpose v1 plus alpha 2 v1 transpose v2 alpha r v1 transpose vr. Right? But because we are dealing with a set of mutually orthogonal vectors, there are terms here to the sum. All the terms will disappear except for one term, right? Because v1 is orthogonal to v2 to vr. That means each of these terms will be zero, because that's the definition of a set of mutually orthogonal vectors. That means what you're left with is alpha times alpha 1 times. Okay? The Euclidean norm of v1 is not zero, right? That means the only way the left hand side and the right hand side will be equal is if alpha 1 is zero, right? So this shows that alpha 1 has to be zero. Now, instead of taking the inner product with v1, if I took the inner product of with vi, then what I end up with is some alpha I, the square of the Euclidean norm of vi is zero. That means alpha I has to be zero. In fact, that is true for all I. Right? That means whenever you have a set of mutually orthogonal vectors, if you take their linear combination, the only linear combination that will produce a zero vector is if we set all the alphas to zero. Okay. So yes. So answer to this is yes. And this is the demonstration or the proof as to why that is in fact true. Right. So that is if you have a set of orthogonal vectors, right? If in addition, so we know the condition is vi transpose vj equals 0 when I is not equal to 0, and vi transpose vi is essentially greater than 0. Essentially, we are basically saying you cannot include the 0 vector in this. Now, instead of vi transpose vi being greater than 0, if we impose the condition that vi transpose vi must be equal to 1, or the Euclidean norm of each vector has to be 1, then what you have is not just an orthogonal set of vectors, but you have a set of orthonormal vectors. You essentially normalize the length of each vector. Let's go back to our previous example, and I ask you, is this an orthogonal set of vectors? Yes, we just saw that earlier. Is this an orthonormal set? Yes? No, okay. All right. How will you convert this into an orthonormal set? Or can we convert this into an orthonormal set? No, okay. Okay. Let me ask you this. What is the Euclidean norm of V1? So Euclidean norm of V1 is square root of V1 transpose V1. Tell me what that is. What about this? So this will be the same. Just do the inner product. Yes. Yeah. Square root of 2 again. Okay. So clearly these don't have length 1. Well, one simple way to convert this into an orthonormal set of vectors is you take the first one multiplied by 1 by root 2, take the second one, multiplied by 1 by root 2, then this will be a set of orthonormal vectors. Okay, because their inner product will be 0 and their Euclidean norms are 1. Okay. So now let's say I have a set of vectors v1, v2, vr, and this is a orthonormal set of vectors. Okay. Now I do a span operation. I'm going to call this set capital V, span of V. What is the definition of a span of a set of vectors? It's simply the linear combination of the individual elements in the vector. Okay. Does the span of a set of vectors form a subspace of, let's say, the individual vectors, right, are from Rn? Does the span of the set of vectors V form a subspace of Rn? Yes. So it will form a subspace. Okay. So it turns out that this is a subspace. I'm going to call it SV. This original set of vectors that you started with V, in this case, will essentially form an orthonormal basis for. So that's what I've said here. If you had an orthonormal set of vectors, that set V will form an orthonormal basis for the span of V. Okay. What is an orthonormal basis? Or what is the basis? Let's start with that. When I say a set B is a basis for some subspace SB, what do I mean? What can you say about that set B? We know two things. Well, we know a couple of things, right? We know it's linearly independent. Well, here that set B is linearly independent. We know that the set B spans the subspace. I mean, it's kind of trivial because SB was defined as the span of B, so but it spans. And because these two are satisfied, any vector in SB can be represented as a unique linear combination of elements of. If I choose an element W that belongs to SB, I can write because W is in SB. SB is the span of the elements of span of the set B. That means W can be produced as a linear combination of the elements of B. And let's say that linear combination is beta 1 V1 plus beta 2 2 beta R VR. I've essentially assumed V1 to VR are the elements of the set B. If B is a basis for the subspace, then there is only one set of betas. Set of values for beta W using V1 to VR. If B was linearly dependent and SB was still the span of B, then there are infinitely many ways in which you can represent W using the elements of B. If that is confusing, then you have to go back to the first module and revise. Okay. So the point I was trying to make was if you have an orthonormal set of vectors, then that set is also an orthonormal basis for the subspace, which is the span of the original set V. So that is about orthogonality between vectors, orthogonality for a finite set of vectors. It turns out this idea can be extended to subspaces as well. And subspaces will have infinitely many vectors. Okay. Let's assume that we have two subspaces. Okay. Let's say our parent space is Rn. Okay. And we have two subspaces V and W. Okay. We can say that this two subspaces are orthogonal to each other. Earlier we were talking about orthogonality between vectors. It turns out you can talk about orthogonality of subspaces also. Okay? And the definition is fairly simple. You can say two subspaces U and W are orthogonal to each other if and only if I choose an element from from V, if I choose an element from W, and I take their inner product, that inner product comes out to be 0. That means if I take any element from U, any element from W, those two vectors would be orthogonal to each other, irrespective of what element I choose from V and W. If there is at least one pair of vectors which are not orthogonal to each other, which you choose from V and W, then the subspaces are not orthogonal to each other. And that's essentially what is written down here. If V and W vectors are orthogonal to each other, where V is an element from the subspace V, W is any element from the subspace W, then we say the two subspaces V and W are orthogonal to each other. Earlier, when two vectors are orthogonal to each other, let's say V1 is orthogonal to V2, then we would usually write it like this. This essentially means if you take the inner product of V1 with V2, you'll get 0. If two subspaces are orthogonal to each other, then you simply write subspace V orthogonal to, this symbol is called perp symbol. V perp W simply means the two subspaces are orthogonal to each other, which essentially means all the elements in one are orthogonal to all the other elements in the other. Let's look at some examples. We're talking about R2. Is the red line that I've done, is that a subspace of R2? Yes, all lines passing through the origin form a subspace of R2. I call this the V subspace. W subspace. Let's say these lines are perpendicular to each other. Okay? If the two lines are perpendicular to each other in R2 and they are subspaces, then you would say, in fact, the subspaces are perpendicular to each other. Okay? Now, if you talk about R3, let's say I take the XY plane. Okay? Does the XY plane form a subspace of R3? I'm talking about R3. Let's say I have the XY plane, X, Y, Z. The floor. Does that form a subspace of R3? Yes, planes passing through the origin form a subspace. Let's say I call that V. The Z line, right? Does that form a subspace of R3? It is. What is the difference between the two subspaces? No, okay, we'll be more explicit. What is the dimension of the XY subspace? The V subspace. You're right. It's a two-dimensional subspace. Why is it two? No. What is the definition of the dimension? What is the definition of the dimension of a subspace? It's a number of elements in the basis set, right? So you only need two vectors which will be linearly independent that will span all of. So that's why it's two. The Z line, its dimension is 1. Okay. Nevertheless, we have two subspaces. Are these two subspaces orthogonal to each other? The two are subspaces, so they have to pass through the origin. The question is, let's say this is the W subspace, that's floor, and the Z line is the V subspace. is V perpendicular to W. That means are the two subspaces perpendicular to each other? Well, the way you verify is, well, if I take any vector from any element from that line and any element from my plane, will they be orthogonal? It will turn out that they will always be orthogonal. Okay, all right. Now let's consider another example. What about the X line? That's a one-dimensional subspace of R3. And the Y line, that's a one-dimensional subspace of R3. Are these two orthogonal to each other? You have to check if you choose any pair of vectors, one from the X line, one from the Y line, will they be perpendicular to each other? It will be. Okay. You can verify that later. Okay. In fact, one way to verify that, if you say the V subspace is the line passing through the x-axis, right? It will be of this form. The subspace where y that passes through the y-axis, well, I'm going to call it beta. So this is the any vector from the x w subspace. This is any vector from the w subspace. If you take their inner product, it will definitely be 0. Okay. Similarly, the first example that we looked at was any element from the xy plane will be of this form. Right? Any element from the z line will be of this form. The inner product of these two will always be 0. Any vector you take from V will be orthogonal to any vector you take from W. Okay. Let's look at a third example. Let's say we have the XY plane and the YZ plane. Two-dimensional subspaces from R3. Are they orthogonal to each other? Are the two subspaces orthogonal to each other? Okay, correct. They're not. Why? Give me an example. If you're saying no, you'll have to give me an example. So yeah, good. Yeah, let's write it down. Say the first one is the XY plane. It will be alpha beta 0. It will be gamma delta. Here you're not guaranteed that they will always be perpendicular to each other. What if if you multiply these two, you will get, if you take the inner product, you'll get beta gamma. Well, if beta and gamma are non-zero, then you get non-zero. That means they are not perpendicular. In fact, the two planes, you would say, or the normals to the two planes would be orthogonal to each other, but the two subspaces are not orthogonal to each other because they have any line, any vector that you choose along the y-axis will be in the xy plane, will be in the yz plane, and a vector is not perpendicular to itself. Right? It will not be 0 unless it's a 0 vector. So you can find vectors in these two subspaces. If you take their inner product, you won't get 0. That's the point. Okay? Right? So that's the definition of when two subspaces are orthogonal to each other. In fact, we can go one step further. If you have two subspaces, okay, we talked about, so in the first module, we talked about sum of two vectors, how to add, or when you talk about a vector space, the addition between two vectors is defined. Then we said, well, we can also talk about sum of two subspaces. You remember? What is the definition of the sum of two subspaces? If you add two subspaces, do you get a subspace? Yes, you do. The sum of two subspaces is, so if you have a subspace S1 and a subspace S2, let's say both of these are subspaces of some parent space Rn. When you say you're adding two subspaces, this is essentially a set of vectors x1 plus x2 such that x1 is from S1. It's trivial. You're simply saying when you say you are adding two subspaces, you're simply taking all the possible combinations of vectors from the two subspaces and adding them together and putting into another set. That's the definition. And you can verify that this is in fact a subspace. This will be a subset of Rn, and it will also satisfy the properties of a vector space. Okay. Right. Now, if we have two subspaces that are orthogonal to each other, and if the sum of those two subspaces gives you your original parent space, right? Let's say we have V and W, okay, which were subspaces of Rn, and let's say the sum of V and W actually gives you Rn. Okay? You add the two of them together and you get all of Rn. The two of them together so you can think of it as the two subspaces together span all of Rn. Earlier we talked about a span of set of vectors. Now I'm informally or very loosely using the term and extending it to subspaces as well. If you add two subspaces, then you're kind of now getting all of Rn. So you can kind of spanning all of Rn. So if this is true, that the sum of the two subspaces gives me my original parent vector space. And if the two subspaces are orthogonal to each other, then you would say that the two subspaces of Rn are orthogonal complements. Okay? Which essentially means that they span, you can get all of Rn from these two subspaces, and they're also mutually perpendicular to each other. In fact, we could have defined complementary subspaces earlier. I don't think we talked about it before. So in fact, if you have two subspaces S1 and S2, okay, which are subspaces of Rn, and let's say S1, no, for that. The two of them together will produce all of Rn. And if S1 the intersection of these two subspaces is 0. That essentially means they don't have anything in common. Okay. If these two are satisfied, then we say S1 and S2 are okay. S1 and S2 are complementary subspaces of Rn, which basically means the two subspaces have nothing in common, and together they'll form all of Rn. Now here, let's come back here to this example. To V and W, are they complementary subspaces? Yeah, if it says, you'll have to argue that they satisfy both of these conditions. Can you get any vector in Rn? If you add these two subspaces, will you get all vectors in Rn? You will, right? For example, you choose one element here, the sum of those two will be this element. If you want to check if this element exists in the sum of V plus W, you can draw a parallelogram such involving the lines corresponding to V and W as two of the sides, and you can reach that point. So the sum of U and V will give you all of R2. Are they complementary? Yes, they only intersect here, right? So that means both these are satisfied. That means B and W actually form complementary subspaces. What about R2? Well, I can say R2 is a subspace of R2. Okay? And V. Do they form complementary subspaces? No. For complementary subspaces, there is no perpendicular. Here, I'm only focusing on this now. I'm only asking if it's complementary. I'm not asking if they are orthogonal complements. Yes, so it's not. The sum of these two will still produce R2, but the intersection is what? No. Not any point. Intersection of these two. intersection is just V because V is in R2. Okay? So this is not equal to 0. That means they are not complementary subspace. Okay. Now, here V and W were complementary subspaces. Are they also orthogonal complements? V and W are complementary subspaces. I'm asking, are they also orthogonal complements? They will be orthogonal complements if they are perpendicular to each other. In this case, we saw they are perpendicular to each other. So in fact, here, in this particular example, V and W are orthogonal complements of R2. In the R3 case, the XY subspace and the Z subspace, do they form orthogonal complements? Yeah, if I can produce any point in R3 by taking an element from the XY plane and taking another element from the Z line, and then I can produce that point. And the two subspaces are perpendicular to each other. That means they must be orthogonal complements. In fact, it's trivial to verify. If two subspaces are orthogonal to each other, their intersection is also only 0. Because every other vector is actually perpendicular, so they are not common. The only common vector is the 0 vector. Okay, right. So that's X and the Z line. What if I take the X line and the Y line? Are they complementary subspaces to start with? The X line, one-dimensional subspace, and the Y line. Are they complementary subspaces of R3? No. Okay. R2 and R3 are not related. They're completely different subspaces. What you're trying to say is, if you add the X subspace and Y subspace, you will get the XY plane, but not R2. That's not R2. That is simply a subspace in R3. Okay? All right. All right. Your intuition is correct. If I add, their intersection is 0. The X line, X subspace, and Y subspace. So the second condition is satisfied. But the first condition is not. If you add the two of them, you don't get all of R3, you only get the XY plane. So they are not complementary subspace. What about the XY line and the XY plane and the YZ plane? Are they complementary subspaces? No, just verify the condition. There are two conditions you need to verify. And tell me both of them are satisfied. They are. If you add the two elements from the sum of the two subspaces will produce R3. Is the intersection 0? The XY subspace and the YZ subspace. And visualize it, right? You have the XY plane and then you have the YZ plane. Do they only intersect at 0? No, they have the entire Y line in common. So the intersection is not 0, so they are not complementary subspace. The sum produces R3, but the intersection is non-zero. That means they're not complementary subspaces. If they're not complementary subspaces, there is no point in talking about asking if they're orthogonal complements. Okay? Right. So you get the idea. Okay. I'm hoping this won't confuse you. Let's say we are only talking about the XY subspace. Okay? Do the X line and the Y line subspaces, do they form complementary subspaces of the XY plane in R3? Remember, see, I'm not talking about my parent space is not R3 anymore. My parent space is now the XY plane in R3. Okay? The X line and the Y line are subspaces of that vector space. They're also subspaces of R3, but they're also subspaces of this smaller subspace, smaller vector space in R3. Do the X line and Y line do they form complementary subspaces of the XY vector space? XY is this, the floor. It's embedded in R3, but we are only worried about R3. This is plane in R3. And there is X subspace and a Y subspace. They form an orthogonal, they form complementary subspaces, right? If you add the two of them, you will get the XY plane, anything in the XY plane, and they only intersect at 0. That means they do form complementary subspaces, but not of 3, but the subspace in which they are embedded. Okay? Are they also orthogonal complements of xy plane? Yeah, they were perpendicular. They are perpendicular to each other. So yes, they are in fact orthogonal complements of not R3, but the subspace in which they are embedded. All right. Now, whenever you have orthogonal complements, we often write them like this. Whenever you see something like this, where V superscript perp equals W, that simply means V and W are orthogonal complements of some parent vector space from which they are. In a way, we are saying, well, if you kind of flip the V subspace so that you make it perpendicular to V, then what you get is W. And of course, this is trivial. The orthogonal complement is the original vector space itself. Okay, all right. So those are some basic ideas about orthogonality of vectors and also subspaces, and this idea of complementary subspaces and orthogonal complement. Okay? And all of that essentially now leads us to the next idea, and a very important idea, which is orthogonal projection onto subspaces. Let's say we restrict our attention to R2. Let's say we have a vector A. Okay? Using that vector, I can generate a subspace, right? Which I call span of a set which essentially contains only the vector A. That will produce this red dashed line passing through the origin. Okay. Let's say I have another vector B, okay, some other vector in R2. We define a new vector B, which we say is the orthogonal projection of B onto A. Okay. If it satisfies these conditions, P will fall in the subspace spanned by A. That means essentially P will be a component. P will belong to the subspace spanned by A, and the difference between B and P. B is the original vector that you started from. You computed P from B, and we'll say P is the orthogonal projection of B onto the subspace spanned by A, if P belongs to the span of A, and the difference between B and P is perpendicular to A. Okay? That's essentially what I've drawn here. Okay? Here, the way it's drawn, P is the orthogonal projection of B onto the subspace spanned by A. Okay? Now the question is, how do we find out? Let's say we are interested in finding out P from, you're given A and B. And we need to find P, which essentially satisfies these two properties. Okay? Well, if I give this to you geometrically, you do it easily, right? You know A, that means you know the line subspace of A. You'll simply then drop a perpendicular line. The difference between B and P is this vector. And you'll simply go to the tip of B, drop a perpendicular onto this line, and then see where this line intersects the subspace spanned by A, and then you will say this is the vector. That's the geometric version. The question is, how do you do it algebraically? Well, we essentially use this idea. All we know is that B belongs to. So when I say, so the first condition was that P belongs to span of the span. No, it's a one-dimensional subspace. That means all elements of this subspace, right, will be of this form. They'll simply be scaled versions of A for some appropriately chosen alpha, right? Because we know here, if this is A, P has to be some alpha times A. All right, this we know. That's from the first condition. The second condition is B minus P. Okay. What does this translate to algebraically? So this is geometrically we're saying they're perpendicular to each other. What is the corresponding algebraic expression for that? But their standard inner product is 0. That means P minus P transpose A is 0. Right? But we know that P is alpha times A. Right? So essentially that's what I've written here. Because A is perpendicular to the difference between B and P, this whole thing has to be equal to 0. But we know P is alpha A. Right? So if you expand this out, then you get A transpose B minus alpha times A transpose A will be equal to 0. That means your alpha is essentially this. And you can verify that is in fact a scalar. Okay? Because here, inner product scalar, so the whole thing will come out to be a scalar. Right? That means if we choose alpha to be A transpose B divided by A transpose A, and you multiply your original vector A by the scalar, you'll get your vector P. Is that clear? Okay. Now, if you look at this vector P, right, it's written as A transpose B divided by A transpose A to A. The denominator is a scalar. I'm going to take that out and I'm going to write it as A transpose A like this. Okay. The numerator is this. A scalar multiplied by vector A. Okay. Now, because this is a scalar, I can write it as alpha A or A alpha. I can move the scalar around. That does not change anything. So if I do that, if I do A transpose A, and I move this around to, sorry, not like that. I do A multiplied by A transpose B. And remember, when you do matrix multiplication, the order in which you do this, if I do ABC, I can multiply AB together first and then multiply the result with C, or I can multiply BC together first and then multiply the result with A. That means I can move this parenthesis around. So if I move the parenthesis around, I can say I'm going to do this. I'm going to do A transpose first, and then I'm going to multiply that with B. If you notice, right, this whole thing will produce a vector. Okay? This also produces a vector. Here, it was a scalar multiplied by a vector. Here, it was a vector multiplied by a scalar. But what this will also produce a vector. But what is this? What will the term in the parenthesis produce? In fact, there is a term for that. We've seen what a vector column vector multiplied by a row vector. What does that correspond to? No, row vector multiplied by a column vector. That is your inner product. Well, both of them have to have the same. No, that's the inner product. Here, if I have a vector A, this will give me the Euclidean norm. But if I have two vectors like this will give me some scalar, provided x and y belong to the same. That is row with a vector, a column. What if you do this? Column with a row, what do you get? This is the inner product. What is x, y transpose? This is the outer product. What do outer products produce? Inner products produce scalar. What do outer products produce? I'll just write it down. You know the shape. This is n cross 1. This is 1 cross n. What will it produce? Well, it will produce an n cross n matrix. But outer product produces matrices. So in fact, here it was a 1 cross 1 multiplied by n cross 1. This was n cross 1 multiplied by 1 cross 1. What you end up having here is n cross n multiplied by n cross n. And all of them will produce an n cross 1 vector. So now if you rearrange terms, right? If you do A transpose, that's the matrix, divided by A transpose A. We can do divided by because the denominator is a scalar. You don't have a divided by B operation. There is no division operation defined for matrices. So this whole thing will still be a matrix, okay? Multiplied by B, and that will produce my orthogonal projection of the vector B onto the subspace spanned by A, right? And this matrix that is here, A transpose divided by A transpose A, is essentially called the orthogonal projection matrix onto the subspace spanned by the vector A. Okay, so if you have the vector A and you compute this projection matrix P, now if no matter what new vector that I give you, B, right, you should be able to then quickly compute the orthogonal projection of that vector B onto the subspace spanned by the original vector A. Right? All you have to do is take that vector B, post multiplied by the projection matrix, and then you will get P. So that matrix P essentially does this geometric operation of, so when we wanted to find the orthogonal projection using geometrically, what did we do? We went to the tip of B, we then dropped a perpendicular line that intersected with the subspace spanned by A, and then we found where that intersection was, and then then we said that is the tip of the orthogonal projection vector, right? Vector P. That whole geometric operation is essentially now done by this, the orthogonal projection matrix. That does the job for you and gives you that vector P. Okay, now maybe let's do a couple of examples. சரி ஓகே ஓகே ஆல்ரைட் தேங்க்யூ அப்படியா சைன் கொடுத்துறேன் alright. Let's do, maybe we have time to do one example and then we'll stop there. This is my A vector. Let's say A is What is the orthogonal projection matrix P? I'm going to call it A onto the subspace spanned by A. Well, this is simply A transpose divided by A transpose. Okay. Tell me what that matrix will be. Okay, that will be the numerator. And there is also denominator. 2. That's it. That's the orthogonal projection matrix onto the vector space onto the subspace spanned by 1 1. Okay. Now, if I give you a vector B, it is 2 1. What is, now that you have the projection matrix, you can easily do it. You can quickly do it. What is it? 1 by 2. 1 by 2 will be there, right? You don't have to take it in. Yeah. You're just multiplying a matrix and a vector. Why are you so confused? What is it? 2, is it? This small vector P is essentially the projection matrix multiplied by B. That is capital A multiplied by this B vector. PA is half 1 1 1 1. B is 2 1. I will get okay. See, and the vector that comes out, right? The two components of that vector have to be the same, right? Because it's a vector in the span of A, and elements from the span of A will always be of this form. But the two elements are the same because all of them are scaled versions of this. Is it clear? Okay. All right. Let's do another example. Let's say my A now is 2 1. What is my projection matrix? What is it? There will be a scalar. Fine. Okay. For 1. Okay. I don't know if that's correct, but let's verify. Let's say now my B is, I want to find the orthogonal projection of this vector onto the subspace spanned by 2 1. What will be the P vector? So there will be PA multiplied by B, be 1 by 5, 4 1 2 1 1 1 Yes. Okay. What will you get? Yeah. The first element is 2 times the second element. It has to be like that because here our original vector is 2, 1. All the vectors in this subspace spanned by A will be 2 alpha alpha. Let's say my B now is, tell me what is B. The same. PA is the same. We're considering still orthogonal projections onto the subspace spanned by this. I've just changed B. So it'll be the same. It'll be 1 by 5, 4, 2, 2, 1, minus 1, minus half. Okay. 1 by 5, minus 5. And it's 2.5. But what is that equal to? Weird. Why did it come out to be the same? You take a vector, you do the orthogonal projection, and this thing is giving me the same vector again. When would that happen? Well, first of all, can that happen? Geometrically, when would that happen? No, geometrically explain. Maybe you can tell me from that. It turns out P is equal to B in this particular last example that we saw. My question is, can that happen? Have we done something wrong? If you think that is okay, I'm asking you, under what conditions does something like that happen? Well, I've brought up this picture so that you can geometrically say when B will be equal to P. No, here, if I do this, right, this will produce the same. So essentially now we are saying, well, it looks like two different B's will give me the same orthogonal projection. That's what you said if it's an opposite side. This is what you meant, right? So that's not the answer. What we are looking for is, if I orthogonally project B, I get B again. I mean, I'm sure you know the answer. You're probably just hesitant because you're unsure. What is it? A and B are? Oh, good point. Okay. What will happen if A and B are perpendicular? That's actually another interesting scenario. Well, do it geometrically, right? Don't bother yourself with algebra now. That's why I brought up the picture. Geometrically, if A is orthogonal to B, sorry, if B is A is orthogonal to B, what will be the orthogonal projection? Well, how do you do it geometrically? You go to the tip of B, and then you drop a perpendicular from the tip of B such that it intersects the subspace spanned by A. Where will the intersection be if B is perpendicular to A? When you say B is perpendicular to A, right, you're saying B is like this, right? If I go here and drop a perpendicular, where will it intersect with the dashed red line? At the origin. That means you will get the zero vector. So that's another one. So if here, when you choose vectors that are orthogonal to the subspace, the orthogonal projection is zero. But what I am asking is different. When will the orthogonal projection be equal to the original vector itself? Exactly. If B was in the original subspace, the orthogonal projection is simply no line at all. You already are in the space. So whenever you choose elements from the subspace, the orthogonal projection will give you the same vector. Okay? So in fact, we through this discussion, we've looked at three things, right? Cases where the vector goes in and comes out unchanged. That is when the B vector was in the original subspace to start with. The case where the orthogonal projection is zero whenever the vectors are perpendicular to the subspace that you're dealing with. And we also saw that there are multiple vectors that will give the same orthogonal projection, like these two. In fact, any of these vectors, there are infinitely many vectors, all of them will give you the same P, same orthogonal projection. But we'll stop here and then we'll continue on Monday. Thank you.